Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS ISC. It's my pleasure to introduce today's speaker, Dr. Shubhada Agrawal. She will be speaking on Markov chain variance estimation, a stochastic approximation approach. Dr. Shubhada Agrawal is a postdoctoral researcher in the Department of Statistics and Data Science at CMU. Before this, she was a postdoctoral fellow in ISYE at Georgia Tech. She completed her PhD in Computer and System Science from TIFR Mumbai and her undergraduate degree in Mathematics and Computing from IIT Delhi. Her research interests lie broadly in applied probability and sequential decision making under uncertainty. Before we move on to the talk, we would like to request our audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for question, feel free to unmute yourself and ask directly or type them in the chat box. We will relay your questions. Over to you, Dr. Agrawal.
Thank you for the introduction, Ankita, and I thank the organizers for giving me the opportunity to speak in this seminar series. I am very happy to be speaking at IISc. Today, I'll be talking about estimating the variance of a Markov chain. It is a very recent work, and this is the first time I'm talking about this. So I'm looking forward to hearing any comments or feedbacks that you may have. This is joint work with Prashant, who is a faculty in Computer Science Department at IIT Madras, and Shiva, who is my postdoc mentor, who was my postdoc mentor at Georgia Tech. So the talk will be in 3 parts. In the first part of the talk, I'll introduce the problem in simplest setting of a finite state discrete time Markov chain. This part will contain all the main ideas and design principles. The other 2 parts will be brief. In the second part, we will see an extension to a more general setting. And finally, in the third part, I will conclude with an application in reinforcement learning. If at any time during the talk you have any questions, please feel free to unmute yourself and ask. I'll be happy to take questions as we go along. So let's get started. Suppose you have a sequence of observations x1 to xn, and you are given a function f. Let us recall some limit theorems in these 2 settings. For the left half, we will assume that x1 to xn are consecutive states of a Markov chain that mixes geometrically fast. In the right half, these are assumed to be independent and identically distributed according to distribution P. From law of large numbers, in the right, we know we have this convergence to mean of f. Similarly, from law of large numbers for the Markov chain or the ergodic theorem, we have the convergence to stationary mean of f on left. We also know that central limit theorem holds for IID setting, where the limit of this summation scaled by square root n is a Gaussian distribution with parameters mean and variance of f. Similarly, we have a central limit theorem on left, where the limit is again Gaussian, with parameter stationary mean of f and variance stationary variance, right? No, actually that's not correct. That's wrong. The variance in the limiting Gaussian distribution in this case will be the limit of variances, which equals stationary variance plus a covariance term. This covariance term was 0 in the IID setting because of independence. But here in the Markovian setting, this cannot be ignored. Let us remove the IID setting for now and work with the variance in Markov setting. After some algebra, it can be shown that the variance term is actually this infinite summation, which captures the covariance of k step apart variables for each k. This can be rewritten as the last expression, where k equal to 0 corresponds to the stationary variance. Since there was only one of these earlier, and now the first term contributes 2 terms to stationary variance, we subtract 1 stationary variance to maintain the equality. Kappa f is also referred to as asymptotic variance, since it is the variance that appears in central limit theorem for Markov chains. In this work, our goal will be to estimate asymptotic variance of f from the observations x1 to xn, where the asymptotic variance, or kappa f, is given by the limit on right. We also saw this that it equals this second expression. Estimating asymptotic variance is a classical problem in statistics and simulation. It is used in statistical inference of stationary mean of a Markov chain. It is also used in analyzing outputs of a Markov chain Monte Carlo experiment and deciding stopping times for such experiments, etc. Towards the end of this talk, we will also see an application in reinforcement learning. Let us look at some natural approaches for this problem. First, we can re-express kappa f in the expression on the top by rescaling it as above. Now, consider a long trajectory of observations, x0 to xn. A natural intuitive approach is to first get several samples for this random variable, which I have highlighted in red on top, and then compute the empirical variance of these samples and scale it appropriately. To do this, for a fixed k or for a fixed batch size, first divide the observations into non-overlapping batches of size k each. These correspond to the blue brackets in the figure. Then compute the empirical mean for each of these batches. Now sample variance of these B empirical means scaled by the batch size is the classical batch means estimator. Here, for this estimator, a fixed batch size contributes to bias of the estimator, since we are truncating the infinite summation in the definition to a finite summation. Furthermore, the number of batches contributes to its variance. Larger the number of batches, smaller would be the variance of the estimator. In the table on top, we note down the mean square error of the estimator, its memory requirement, and if it is an online estimator or not. In fact, it has been shown that batch means estimator with properly chosen batch sizes converges to the true variance at the rate of order 1 by n to the 2/3 in the mean square error sense. For this, the batch size k needs to be a function of n, the total number of samples. This means that whenever a new sample arrives, the batches need to be redefined and the estimator needs to be computed from scratch. Hence, it is not an online estimator. Further, since this recomputation requires storing all the historical samples, its memory requirement is also order n. Another closely related estimator is the overlapping batch means, which is same as batch means, except that the batches are now no longer non-intersecting and are chosen as displayed in the figure. They are maximally overlapping. However, it has been shown to have similar properties as batch means estimator. A few other batch estimators have been proposed that vary in the way they estimate within each batch and how they combine information across the batches, with guarantees as displayed in the table. Next, jackknifing is a popular technique to reduce the bias at a price of increased variance. Using appropriate jackknifing, the performance of these previous different batch estimators has been shown to improve to achieve a rate of order log n by n in mean square error. However, these jackknifed estimators are also not online and have large memory requirement. In 2009, Wu et al. Proposed a recursive version of the classical batch mean estimator, where the estimator is online with order 1 memory requirement. However, it has a slow rate of convergence of order 1 by n to the 2/3. The question we are interested in is, can we achieve the best of both these worlds? Can we achieve the optimal rate of log n over n and can we achieve the estimator, which is online and has small memory requirement. In this work, we propose a linear stochastic approximation based estimator that at each time takes in 3 inputs. The first are the observations at the current step. The next is the estimator from previous time step, and a few other auxiliary estimates from time step n-1. It performs order 1 recursive update using these inputs and outputs the updated estimates of the variance and the auxiliary variables. Moreover, it achieves the order 1 by n rate of convergence in mean square error. So to highlight, our estimator has optimal order 1 by n rate of convergence. It requires order 1 memory, and it is online. Before presenting our estimator, let me first present the key ingredients that go into the design. We saw that simple estimators based on this expression of kappa displayed here, they suffer from huge bias due to truncation of the limit. This leads to suboptimal rate of convergence in mean square error. We also saw this equivalent formulation, but this might also suffer from similar drawbacks because of presence of this infinite summation here. Instead, we use a third formulation. First, observe that the stationary variance can be expressed as the expression in bottom. This is just by definition. Variance of f equals expected value of f square minus expected value of f whole square. Next, the first term, for the first term, the infinite summation of covariances can be shown to equal average of a product of 2 functions. Here, V is a vector that solves the fixed point equation on left, or the so-called Poisson equation. Let us take a brief detour to get some intuition about Poisson equation and how this infinite summation manifests in the solution V. We will come back to this slide later. So Poisson equations are also commonly known as Bellman equation, which might be a little more familiar term. So here on top, we have the fixed point equation on top. This can be rearranged as shown above. Now, if I minus P were an invertible matrix, then we know the solution. That would be I minus P inverse times the inverse of I minus P times the right-hand side. However, since P is a stochastic matrix, I minus P is not invertible. But recall that the Markov chain is ergodic. That is, it mixes geometrically fast. And hence, the n-step transition matrix converges to the matrix of stationary distributions geometrically fast. This convergence implies the geometric convergence in the last display. Since the sequence converges geometrically fast, the infinite summation exists and can be shown to be a solution of Poisson equation by direct substitution in the above red equation. And this is how the infinite summation manifests in the solution. We can see that a solution of Poisson equation is this infinite summation. By the way, the solution of Poisson equation is also called value function. I might use this term as we go along. So now let's get back to our ingredients for estimator design. So we saw that the value function has an infinite summation. So now we use this formulation of kappa for our estimation, for our estimator design. And we also have that this value function solves the Poisson equation, which we will use to estimate V in the estimator, in the overall estimator. So let's keep these 2 ingredients with us. Next, I just use linearity of expectation to combine the 2 terms in kappa f into a single expectation. Now observe that if V is a solution to Poisson equation, the equation in middle, then any v plus a constant multiple of all one's vector or a constant shift of v is also a solution. Thus, the solution space of Poisson equation is a line parallel to all one's vector. However, observe that the choice of v does not affect kappa f, because the contribution of this constant shift cancels off. This can be seen from the blue term in kappa f equation, where the contribution of this constant shift cancels off. So recall v bar was expected value of v under stationary distribution. Okay, so now the idea is to estimate kappa using the first equation, assuming an estimate for v is available, for any choice of v on this line. This corresponds to estimating mean of a function from observations. Now, since this step depends on estimating v or assumes availability of an estimator for v, we will also estimate v using the Poisson equation. This corresponds to estimating a fixed point of a function. For both of these, we use stochastic approximation. So now let's take a quick detour to understand the stochastic approximation for these two problems, mean estimation and fixed point estimation. Okay, so on left, we have the mean estimation problem. Suppose we want to estimate mean of a function g from the observations. We all know that empirical mean is an estimator, and it can be written as this expression over here, which equals this expression at the bottom. This is just simple manipulations. However, there is nothing sacred about 1 by n. I could replace it with any alpha n satisfying certain properties, decaying at certain rate. And this last update is an example of stochastic approximation. We will use this update equation for estimating means for appropriate choice of alpha n, which may not necessarily be 1 by n. Let's keep this equation with us. Now let's look at fixed point estimation for a function v, for a function h, or we want to find a solution v equal to h of v. Suppose you have an oracle access to h, which takes in a point v in the domain of h and outputs a noisy version of h of v. Then the stochastic approximation approach corresponds to this update equation on right, which is very similar to the one on left. So the left-hand side is a special case of the right-hand side. The stochastic approximation update is known to converge to the fixed point as long as h and h tilde satisfy certain nice conditions and for appropriate choices of alpha n, which will be true in our settings. So in short, we will be using these two equations or these two update rules for our estimator. So let's keep these with us. So we had these ingredients, and let's replace the estimations with the stochastic approximation update equations that we just saw. With these 4 ingredients, we are now ready to design our estimator. So recall our estimator, at each time, it will take as input the current observations, an estimate for kappa from previous time step, and some auxiliary estimates from the previous step. It will then perform some simple updates and then output the updated estimate for kappa and auxiliary estimates. For variance estimation, we will use these 2 ingredients of the 4 ingredients from the previous slide. Observe that apart from the observations, kappa depends on these unknown quantities highlighted in the blue boxes. We will need to estimate these, but at the current time step, these are the corresponding auxiliary estimates from the previous step. So at time n, we will use their estimates from the previous step. Okay. Now, using the mean estimation update in the second equation in middle, our estimate for kappa at time step n takes the form in the bottom display. In this big bracket, I'll just pull in the G, which corresponds to the term for which we are taking expectation there. And the blue boxes, for the blue boxes, I have used the estimates from the previous time step, which recall they are the inputs to the algorithm at this time. So these are available with the algorithm. Finally, let us rearrange the terms to arrive at a form that will be useful later. So this is our update equation for kappa at this time. Now, each of these red terms need to be updated. These except for kappa n minus 1. The other three red terms correspond to the auxiliary variables or auxiliary estimates. So let's estimate them now. The update for stationary mean is a simple mean update using the equation in center. And as earlier, it can be rearranged to arrive at this form. Finally, we update V and its stationary expectation, V bar. To do these, we will use two ingredients, the Poisson equation and the fixed point update that we saw for using stochastic approximation. So using the stochastic approximation for fixed point estimation of Poisson equation, we have this update for V, that equation on top. Finally, so again, for V bar, it's just a simple mean update. I won't go into the details. It's just simple mean update. And this is what the overall estimation for V looks like, V and V bar. So observe that policy evaluation or evaluating this value function is the subroutine in our estimator. Overall, at step n, our estimator performs these 4 simple updates, each of which correspond to stochastic approximation, either for mean estimation or fixed point estimation. And overall estimator reduces to this picture here, which at each time takes 3 observations and 4 estimates from the previous time steps, perform constant number of update, and outputs 4 updated estimates. So all in all, this is an online estimator which performs order 1 updates, and it recursively keeps updating at each step. So I'll flash this slide later, but we won't need to go into details of each update equation. So yeah, it has these 4 update equations. Okay, so yeah, any questions at this step before I go into the finite sample bounds? Any questions related to the design?
Yeah, Shubhada, can I ask a question? Aditya here.
Yeah, sure. Yeah, hi Aditya.
So, yeah, this is very interesting. I was curious to know if when you're solving the Poisson equation using stochastic approximation, what kind of conditions do you need on that edge for this to converge? Do you need some kind of contraction? Or?
Right. So yeah, yes. So it's not exactly a contraction because so there are multiple solutions. If it were a contraction, there has to be unique fixed point. So it's not a contraction under any norm, right? Because there are the solution space of Poisson equation, it's not a unique solution. It is a line. So yeah, it will in fact be a contraction in semi-norm, meaning we will contract in the orthogonal direction. And that's what we care about, because in kappa F estimation, it doesn't matter which V we use. We could converge to any point in this line. So what we will show is, yeah, I'll show this in the proof sketch, but at a high level, we will just converge in the orthogonal direction, meaning our iterates will converge to any point on this line, and that suffices for our variance estimation.
Okay, thanks.
Shubhada, my name is Chandra. I also have one quick question.
Hi, Chandra. Yeah.
So in this 4 equations that you showed a little bit later, the update equations, you're
Okay.
using the same alpha in all 4, right?
Right. Yeah.
Do
So
they
I
need
use
to
the
be
same alpha n, but C1, C2, C3, they are just constant multiples of each other. Yeah.
Yeah. Do they need to be the same? I mean, do they need to decay at the same rate, or can they decay at different rates?
Yeah, it's an interesting question. So with using these same alpha n's, same rate, there for the appropriate contraction, we need some conditions on these C1, C2, C3. But maybe if we have this multi-time scale, if they decay at different rates, we may be able to get rid of the conditions on step sizes that we need. But then it's an open question, like how to get finite sample bounds for such different time scale algorithm.
Okay, thank you.
Thanks. Any other question at this step?
Quick question. This is Partha.
Yeah.
Is H linear or is H non-linear?
Sorry, which H? In the
H in the fixed point.
estimation, in the
Yeah.
fixed point. Yeah. So it depends. Yeah. Right now, it could be anything. But here we are using only linear updates. In the fixed point, so for the fixed point convergence, H need not be linear. It could be anything as long as it satisfies certain contraction properties. But in this particular work, we are using only a stochastic approximation for linear.
Okay, thanks.
So for example, here the Poisson equation is linear in V. V is the fixed point, it is linear in V.
Okay, yeah, thanks.
Okay, so let me move forward and let's look at the finite sample bounds. So we develop finite sample bounds for the mean square error of the proposed estimator when the step sizes used by the algorithm is decaying linearly in time. For this particular case, the mean square error takes this form as displayed here. So by the way, in the paper, we also have it for constant step size, but that has its drawbacks, so I'm not presenting that. So as is common in the stochastic approximation results, the first term here is faster decaying. So this corresponds to some conditions on alpha, which is a constant that appears in the step size. So alpha is large enough so that this first term is faster decaying. And the second term is the rate determining term. And from this expression, it is clear that the overall rate of convergence is order 1 by n. Here, constant xi1, it depends on the initialization error, as well as the norm square error of the value function, whichever value function which we converge to. So, yeah, so this value function is a vector in S dimensions. So this has S square dependence. Similarly, xi2 has this dependence. I have not defined what delta 1 is, but it corresponds to some constant that depends on the underlying Markov chain. And it also corresponds to, it is also proportional to some sort of contraction factor for an appropriate operator. Now, to get a mean square error of at most epsilon, if we invert this bound, we see that we require at most these many samples. So here we have at least S square dependency on state space in the numerator. And delta 1 is some parameter that depends on the underlying Markov chain. So before moving to the proof sketch, I would like to highlight that the estimator with appropriate choices of the step size constant C1, C2, C3 is an online estimator. Further, the guarantees on the mean square error are anytime, meaning the guarantees hold for each time n, and the estimator does not require any knowledge of n beforehand. So I'll now go into a high-level proof sketch of this result, but any questions
Yeah,
on-
it's me again, Aditya. So
Yeah.
I was curious to know if you, I mean, how do any of these constants, delta one or these i's and so on, it intuitively looks like it must have some dependence on the mixing time, right? If you had a very, very sticky Markov chain,
Right.
you would need to wait for some time to even get hold of the variance, right?
Right. So delta one depends on like the properties of Markov chain, how fast it is mixing. And so xi1, xi2, so xi2 has delta one dependence. And in the first term, delta one appears in the exponent. So it is very implicit. It's not an explicit dependence. But yeah, so delta one relates to second largest eigenvalue or the spectral gap of the underlying Markov chain.
Okay, all right, thanks.
That's how implicitly it depends on the structure of Markov chain and how it mixes. Yeah, but explicitly, so in our proof, we don't explicitly require mixing of the Markov chain. And if we look closely, that's how we are able to get rid of log n factor. Like classically in Markov chain, stochastic approximation in presence of Markov noise, the rate of convergence that is known as log n upon n. And such proofs, they rely on the Markov chain first mixing and then looking at the convergence. However, in our proof, we don't rely on like we don't explicitly condition on the Markov chain mixing, and we are able to, shave off that log n factor. But yeah, implicitly the bound depends on delta one.
Also, this large enough alpha and h, even to set those, do you need to, I mean, is the optimal choice depending on properties of the Markov chain?
Right. So the theorem statement says that as long as alpha and h satisfy certain conditions, then we guarantee this convergence. Of course, to use the optimal choice, we will need to know some properties of the Markov chain, because alpha and h, their ranges, they do depend on properties of Markov chain.
Okay, thanks.
Yeah. Any other question? Okay, if not, let me present the proof sketch. So the first step in getting the mean square error bound is to formulate the estimator as a linear stochastic approximation. Recall, we had these 4 update equations at time n. We don't need to go into details of these, but we had these 4 stochastic approximation updates. And here the red terms, they correspond to the estimators at each time. So we had 3 auxiliary estimates and 1 estimate for kappa, and those are the 4 terms. Let's squish all of them together. And so these are theta n. Let's call this vector theta n and this theta n minus 1. Now, if you look at the update equations, these are all linear in these variables. So we can write this update as a vector update equation, single vector update equation, which is theta n equal to theta n minus 1 plus alpha n times some a theta n minus 1 plus bn. Here, an is a matrix in which I have dumped all the dependencies on observations and the constants. And bn is a vector. Okay, so at a high level, the algorithm is a linear stochastic approximation update. So once we have this linear stochastic approximation update for, once we have this linear stochastic approximation form of the estimator, if we can prove some contraction of the average operator, suppose we are able to prove such a property that there exists a delta one such that for all the vectors theta, theta transpose expected matrix A times theta is less than, it's negative, then standard Lyapunov drift arguments would give finite sample bounds on linear assay. Okay, but recall we had this. So theta n has this vector v, which is the value function in it as its component. And there is no unique solution to v fixed point equation. There is this line. If we had such a contraction, there should be a unique fixed point to which the iterates converge. But that's not the case here, because the limiting, we know that the limit may not be, in fact, it's not unique because it has this infinite solutions, number of solutions in one component. So instead, what we show is, so we look at this perpendicular space, which is orthogonal to, so it is orthogonal to all one's vector. Now, suppose we have this iterate Vn at time n. We project that onto this orthogonal space, and we look at this distance on this space to V star. V star is the solution, any solution, it's a solution to the Poisson equation that is orthogonal to all ones. Okay, we look at this distance and we show that this converges to 0. In particular, it's a contraction in this direction, or when we restrict the operator on this subspace, then it is a contraction. So in particular, the iterates, they proceed so that this distance reduces to 0. In the parallel space, they may diverge. They may go to any point. We don't care about that direction. So this corresponds to showing that when theta is restricted to an appropriate subspace, then we have this negative definiteness property. Yeah. So I think, yeah, so that's the proof sketch. Okay, so now, in fact, the theorem statement is a little more stronger than what I presented earlier. The guarantees hold for all the estimates. So sum of mean square error for all the estimates, in particular, even for the value function estimation. So we have this bound for all the estimates converging to their limiting points. So this concludes the first part. Yeah, I'm happy to take any questions on this. The next two parts will be brief, and they will mostly be application of what we saw till now. Okay, so if not, let's move ahead. So in the second part, we will consider a Markov chain with large state spaces. So recall that this was a subroutine in our estimator. The policy evaluation part was a subroutine in our estimator. And this requires order state space size of memory, right? Because storing each of, so these V vectors or the estimates are order S. But what if the state space is too large? So to get around this, we compute a lower dimensional approximation for value function, and then use that approximate value to estimate the variance. Okay, so let's look at the setup. Suppose we are given d-dimensional feature vectors. Here D is assumed to be much smaller than S. These feature vectors correspond to the columns in phi matrix on right. Let this blue space be subspace spanned by the columns of phi. Then for any value function V, its best approximation in the subspace is its projection onto the subspace. Let's not worry about the projection in what norm, but its best approximation is its projection. So the idea is to modify the policy evaluation subroutine so as to incorporate this linear function approximation. And this is something standard in reinforcement learning. The algorithm is standard in reinforcement learning. So I don't think I will have enough time to explain that particular policy evaluation with linear function approximation. So I'll skip that part. But once we have, so that part will give an estimate for V, which is like phi times theta V. So this is a projection of V onto this lower dimensional subspace. And wherever we have V appearing in the kappa equation or the kappa estimation, we will replace that by this approximate estimate. Okay, so let's see the mean square error. So this is kappa F, the true bound, so the true variance. And these are the iterates of kappa at each time. So these may converge to some kappa star. which may not be same as kappa f because we are using an approximation to value function. So as earlier, we show a finite sample bound on mean square error between the iterates and the limiting point of this update equations. And we show a bound of order 1 by n. So here kappa star is an approximation of kappa f, where we have replaced the value function by its approximation. And similarly, if we invert this finite sample bound, okay, here I have not displayed the finite sample bound, but it's similar as same as earlier, with appropriately changing kappa star. But if we invert this finite sample bound, to get a mean square error of at most epsilon square, we require at most these many samples. Previously, we used to have S square dependence here. Now we have D square dependence. Now the question is, can we get a bound on this error? Yeah, but that's not hard to see that. Let E denote the distance between, so there is this line of solutions of value functions, and then we have the space, lower dimensional space to which we are approximating. Let E be the distance between these two spaces, or these two sets. So this corresponds to minimum approximation error in V estimation. This is the bare minimum approximation error that we will incur due to this approximation architecture, no matter what algorithm we use. What we can show is that kappa star and kappa f, they won't differ too much if this approximation error in V is small. In fact, it will be 0 if there is at least one point at which these two sets intersect. Again, this bound follows quite simply looking at the expression for kappa. And since it was linear in V, using some manipulations, the bound for error in estimation of V translates directly to bound in error for estimation of kappa. So yeah, that's the linear extension to the linear large state space with linear function approximation. Finally, let's conclude with an application in reinforcement learning. So let me begin by describing the setup. So here, an agent sequentially interacts with a dynamic environment. At time t, the environment is in state st. The agent takes an action according to a stationary policy mu. So a policy is a map which takes in the state of the environment and outputs an action or a distribution over actions. So at each time, the agent acts according to a stationary policy mu. And on doing so, the environment evolves to a new state, st plus 1, according to some transition probability, which may depend on the action chosen. And the agent receives a reward, which I'm denoting by R of STAT. Typically, the performance of a policy is measured based on the long-term average reward accumulated by it. However, it is also crucial to account for risk. So we propose considering asymptotic variance as a performance criteria for a given policy, which is the expression on bottom here. So why asymptotic variance is a natural candidate? So in literature, two notions of variance have been proposed as a risk measure. In Prashant and Gawamzadeh, they use stationary variance as a risk measure. However, stationary variance, as we saw in the first part, it does not capture correlations of the Markov structure present due to the Markov structure. Instead, asymptotic variance is the variance of the random variable whose mean is optimized in the average reward reinforcement learning setting. And hence, it's natural to consider this variance as a measure of risk in the mean variance trade-off setting. Now, this will just be a reduction from the first part, reduction to the first part. So on the left-hand side, we have given a policy, we want to estimate its asymptotic variance. So on the left-hand side, we have the reinforcement learning setting. On the right-hand side, I'll bring back the things from the first part and we will see the reduction. So in the first part, we had x1 to xn observations from a Markov chain and f, which was a function defined on state space. And we had f bar, which was the stationary mean of f, and it can be shown to equal this limit of some expectations. And we had asymptotic variance, which was this expression, which was the limit of variances. Now, for a fixed policy, if we fix a policy, it induces a discrete time Markov chain. So we are assuming that the state space and action space in the reinforcement learning are finite. So for a fixed policy, it induces a discrete time Markov chain on this enhanced state space, which is state cross action. Now, the reward functions in RL, they are functions defined on the state space of this enlarged Markov chain. And with this observation, kappa mu, so the asymptotic variance on the RL side, on the left side, this is the same as the asymptotic variance that we saw in the first part, with f being the reward function here. So thus, using this, so all the theorems that we saw in the first part, we can extend those to reinforcement learning setting for the policy evaluation problem here. Just to give some details. So here, so we saw that we had to estimate value function there. Here that corresponds to Poisson equation for this reward function, which is the Q, state action value function. And it satisfies this is the Bellman equation for the average reward RL setting. And then substitute, this is just substitution from the previous part. Wherever we had value function, now we will have the state action value function here. And the function f is now R of s comma a. That's about it. Yeah. So now again, the same guarantees, we can transport them here, and we get similar mean square error bounds and sample complexity results. So to conclude, we saw an estimator, we saw a linear stochastic approximation based estimator that has order 1/n rate of convergence in mean square error. It was an online estimator and requires order 1 memory. And we saw that the key design ingredients are Poisson equations and stochastic approximation. We extend this in several directions in the paper. We saw a little bit touched upon the linear function approximation. We also touched upon the reinforcement learning. In the paper, we also have estimators for vector valued rewards where we estimate the variance covariance matrix instead of the asymptotic variance. We estimate the matrix. As a byproduct of this estimator, we also get an estimator with similar guarantees for stationary variance estimation and also for IID variance. Yeah, thank you.
Thank you, Dr. Agrawal, for an informative talk. Are there any questions? So if there are no questions, we can close this session. Thank you all for joining us.
Thank you.
And have a great day. Thank you.